Welcome to The Explainer. Today, we're diving into a hidden challenge that honestly makes our entire digital world work: concurrency control. Think of it like an invisible ballet that keeps everything from your bank balance to your social media feed from just completely descending into chaos.
All right, so here's our game plan for today. We're going to start with a really simple, relatable problem. Then, we'll look at the perfect solution that engineers are always chasing. We'll open up their toolbox, see how they manage all the chaos, and then, and this is key, explore why they sometimes have to bend the rules to get more speed. From there, we'll take the whole problem global and wrap it all up by understanding the critical balancing act that really shapes our digital lives.
Okay, so let's start with a situation I think we've all been in. You're online, you see that last item in stock, and you are racing to grab it. The thing is, you're not the only one.
I mean, this is the absolute core of the concurrency problem, right? You've got multiple people trying to read and change the very same piece of data all at once. So who gets the seat? Does the system accidentally sell it twice? Or does the whole thing just crash? The answer here is what separates a reliable system from, well, a disaster.
Now in database lingo, each of those booking attempts is called a transaction. And the most important thing to know about a transaction is that it's an all or nothing deal. The system has to check for the seat, reserve it, and process your payment. If any single one of those steps fails, the whole thing gets wiped away, like it never even happened. This is all designed to keep the database in a consistent and predictable state.
So how exactly do these transactions, run into each other? Well, it usually happens in one of two ways. One person's request might be trying to read the seat's availability right as another person's request is updating it. That's what we call a read-write conflict. Or they could both try to confirm the booking at the exact same instant. That's a write-write conflict. This is basically the digital traffic jam that we have to prevent.
Okay, so how do we solve this? The ideal solution is actually surprisingly simple in theory, even if it's super complex to pull off. The goal is to take all this chaos and turn it into perfect, simple order.
And that perfect order has a name: serializability. It is an incredibly powerful guarantee. It basically means that even if thousands of transactions are happening all at once, overlapping and getting all mixed up, the final state of the database is absolutely identical to what it would be if they had all just happened one by one, in a nice, neat single-file line. No weird side effects, just perfect, predictable results.
So how do systems actually pull this off? I mean, they don't just cross their fingers and hope for the best. Nope. They have a toolbox with three main strategies for dealing with all these conflicting transactions.
You can think of it as a few different philosophies. Engineers can be pessimistic and just make transactions wait in line using locks, kind of like passing around a talking stick. Or they can use timestamps to enforce a really simple first-come, first-served rule. Or they can be optimistic. Just let everyone go at once, and if any transaction causes a problem, you just undo its work. It's the classic ask for forgiveness, not permission strategy.
That wait approach, the one with locks, is probably the most common. And it's usually done with a protocol called two-phase locking, or 2PL for short. And no, it's not about locking something twice, it's about having two very distinct phases for the locks within a single transaction.
Here's how it works. In phase 1, the growing phase, the transaction is like a shopper going through a store, gathering up everything it needs. It acquires locks on all the data it's going to touch. Then it does its work. And only after it's totally done does it enter phase 2, the shrinking phase, where it starts releasing those locks. That simple rule, no grabbing new locks after you started letting go of old ones, that's the magic trick that guarantees serialization. But, of course, there's a catch. This perfect serializability, enforced by all this strict locking, can be slow. It creates bottlenecks. So, in the real world, developers often need to bend the rules a little for better performance, letting just a bit of controlled chaos back into the system.
Now, relaxing these rules can lead to some really weird errors, or what the pros call read phenomena. For example, a dirty read is when your transaction sees data that another transaction changed but hasn't finalized yet. And if that other transaction rolls back, it means you just based a decision on data that never officially existed. A phantom read is even weirder. Imagine counting the number of items on a shelf and getting 10. You look away, count again, and now there are 11. It's like a new row just mysteriously appeared in your data between two identical requests. So to control these trade-offs, databases give you these different isolation levels. You can think of them like dials for consistency. The highest level, serializable, is like a fortress. It prevents all these weird phenomena we just talked about. But as you turn that dial down to, say, repeatable read or read committed, you start allowing some of those issues to happen, and in exchange, you get better performance, more speed.
Okay, so let's really raise the stakes here. Up until now, we've basically been talking about a single database. But what happens when your data isn't in one place? What if it's spread across servers all over the world?
Yeah, the challenge gets exponentially harder in a distributed system. All of a sudden, you're not just worried about two people hitting the same server anymore. Now you're trying to synchronize data between New York, Tokyo, and London with all the network delays and potential failures that come with it.
This is where the famous CAP theorem comes into play. It was first put forward by Eric Brewer, and it basically states that there's this fundamental, unavoidable trade-off that every large-scale system has to make. You've got these three things you want: consistency, availability, and partition tolerance, but you can only pick two.
And the choice pretty much boils down to this. You can't stop the network from failing. That's partition tolerance. And in the real world, you just have to assume it's going to happen. So you're forced to choose between the other two. During a network problem, do you prioritize consistency, where maybe some people get an error but nobody ever sees stale data? Or do you prioritize availability, where everyone gets a response, even if it might be slightly out of date? You literally can't have both at the same time during a failure.
And what's really fascinating is that this trade-off doesn't just happen when things go wrong. Even when the network is perfectly healthy, stronger consistency almost always means higher latency. See, to guarantee that everyone sees the absolute latest version of the data, all the servers have to talk to each other and coordinate. And that coordination takes time, which makes the whole system feel slower.
Which brings us to the final and most crucial point of this whole topic. There is no single best answer here. It is all about making the right trade-offs for the right situation.
The right choice depends entirely on what the application is trying to do. For your banking app, consistency is king. I mean, you would much rather see an error message than an incorrect account balance, right? But for your social media feed, availability is everything. Who cares if a like takes a few extra seconds to show up for everyone, as long as the feed itself loads instantly when you open the app?
You know, it's this constant balancing act between correctness and performance, between consistency and speed. And it's a decision that's made deep inside the architecture of almost every digital service you use, and it fundamentally shapes our entire digital experience. So the next time an app feels just a little bit slow, maybe it's not broken. Maybe it's just taking a moment to get its story straight.